This telescope was no longer on anyone's radar, but Hubble has just confirmed that our physics is broken. The old space telescope initiated the change in physics years ago, but nobody realized it. Edwin Hubble, the astronomer after whom the most successful space telescope of all time was named, brought us a new view of the universe and many subsequent theories about its origin 100 years before the telescope named after him was launched. Later, it was the telescope named after him that called the astronomer's greatest achievements into question. Was Hubble wrong when he postulated the expansion of the universe in 1929? In the 1920s, astronomy underwent a revolution. The first improved telescopes made it possible to look deeper and deeper into the universe. Edwin Hubble was one of the first researchers to realize with astonishment that our Milky Way is not the only galaxy. The astronomers of the time opened up completely new dimensions of a cosmos in which our galaxy is just one of billions, and the true dimensions of the universe slowly became apparent. Before this revolution, people only saw a small radius that barely allowed them to see beyond the Milky Way, and yet that was already a lot compared to the people who, only a few decades earlier, did not even know of the existence of our galaxy. Now we are experiencing such a revolution again, and many scientists do not want to realize that what they thought was real before cannot be the full truth about the universe. Edwin Hubble was one of those scientists who were open to new things and was fascinated by the many newly discovered galaxies. He observed that distant galaxies were clearly moving away from the Earth. This observation laid the foundation for the Hubble constant, which states that the speed of distant galaxies is proportional to their distance from Earth. This discovery was the basis for the idea of the expanding universe. Hubble used the then brand new 100-inch Hooker telescope at the Mount Wilson Observatory to measure the redshift in the spectra of galaxies and determine their distances. These findings influenced the Belgian Georges Lemaitre in his assumptions that the universe originated from a single point. In 1929, Hubble published his work on redshift and the speeds of galaxies, and shortly afterwards, Lemaitre published the theory of the Big Bang. For a long time, both models formed the foundation of cosmology, which is still valid today but is no longer tenable. Hubble brings down his father. The Hubble Space Telescope, of all things, provided scientists with observations that, for the first time, cast significant doubt on the Hubble constant. In the late 1990s, the telescope observed things that contradicted Edwin Hubble's calculations. The Hubble telescope was a revolution when it was launched into space in 1990. For the first time, we were able to look into the depths of the cosmos without the disturbing influence of the Earth's atmosphere. The Hubble Space Telescope was the first to show us impressive discoveries such as the existence of supermassive black holes in the centers of many galaxies, the impressive variety and beauty of nebulae, and the birthplaces of stars. Observations of the brightness of Cepheid variables and type Ia supernovae then led to strange discrepancies with the values of the Hubble constant. The brightness measurements of these events served as an alternative basis for determining distances in the universe, and these measurements led researchers to arrive at a different rate of expansion of the universe. Cepheid variables are stars with a specific relationship between luminosity and pulsation period, and type Ia supernovae are exploding white dwarfs in a binary star system. These supernovae serve as standard candles for measurements as their absolute brightness is known. By comparing their observed brightness with their actual brightness, distances, and thus the expansion rate of the universe, can be determined. And this is where the inexplicable differences to the conventional measurements with Edwin Hubble's methods arose. Later, the Planck satellite confirmed these disturbing observations when measuring the cosmic microwave background, the radiation left over from the Big Bang. Today, we know these measurement differences as the Hubble tension. The tension arises because measurements of the Hubble constant based on local bright cosmic events give consistently higher values than those derived from background radiation data. This discrepancy was the first indication that our physics is at an end. A new physics beyond the standard model. The discrepancy between different measurements of the expansion rate of the universe could now open the window to a completely new kind of physics. The new physics is said to lie far beyond what we know as the standard model of cosmology and astrophysics. But let's first take a look at the world of the smallest particles. The standard model of particle physics is a theoretical construct that describes the building blocks of matter and the forces that act between them. This construct from the world of the smallest particles could normally be successfully transferred to the outcome of experimental research in the world of large material phenomena in the cosmos. However, this explanatory approach failed in the case of the Hubble tension. Of all things, this is a further indication that the Hubble tension tells us far more than just a measurement error. Many scientists are convinced that it must be the solution to a previously unknown component of physics. We have achieved a great deal in the research of subatomic particles, which are the basis of the universe, and yet we still know very little. We know about quanta, quarks, leptons, and bosons, but the interactions and behaviors of many of these particles are still mysterious, and researchers are constantly discovering more particles. Some particles behave so mysteriously that our current models of the fundamental forces in the universe are inadequate to explain them and their effects. Many particle physicists believe that these discoveries in the subatomic realm point to a previously unknown fifth fundamental force. So far, we have based our whole worldview and physics on the four known forces: gravity, electromagnetism, and the strong and weak nuclear forces. It's possible that this knowledge is incomplete. But what effect do these processes in particle physics have on Hubble's tension? The question can be answered quite simply. This new force could act on a cosmic scale and influence the expansion rate of the universe. Until now, the mysterious dark energy has been held responsible for the accelerated expansion of the universe. It's possible that there are as yet unknown particles that interact with dark energy and influence its behavior differently on different scales. It's also possible that dark energy is not constant as previously assumed but has changed over time. Perhaps dark energy is more dynamic than we previously thought, and its variation could explain the discrepancies in the Hubble constant measurements. This would also mean that other physical quantities in the universe can change and are not constant. All these approaches would represent a massive change in our physical and scientific theories. Every discovery that cannot be explained by conventional models can be an important indication of this new physics. This is where the new James Webb Space Telescope comes into play. Its discoveries in the distant past are almost all no longer compatible with the standard model of cosmology. Webb's discoveries break the lambda CDM model. It was a brilliant moment in the history of space exploration when the new James Webb Space Telescope opened its eyes for the first time in the summer of 2022. Based on infrared technologies, this telescope looks even sharper and deeper into space than Hubble. Astronomers were eagerly awaiting the launch of the new telescope, as it was supposed to have the ability to look back to the time when the first stars and galaxies were born in the previously dark cosmos. What the scientists then saw was a shock. Webb's first deep images of the universe show no trace of a young universe with gigantic protostars or the first chaotic dwarf galaxies. Instead, Webb shows an astonishing number of perfect and very luminous galaxies at a time when the universe should actually still be completely dark. Galaxies such as Glass Z13 or Maisie's galaxy existed 200 to 300 million years after the assumed Big Bang. However, galaxies of this order should only have appeared 3 to 4 billion years after the Big Bang. Webb also discovered gigantic black holes that are so large that our Sun would fit into them a billion times. They also do not fit into a young universe in which only larger matter objects are likely to form. The observations contradict the lambda CDM model, which is based on the findings of the general theory of relativity, observations of the cosmic microwave background, and the large-scale structure of the universe. The standard model explains the nature and evolution of the universe through 6 parameters, including dark energy, lambda, and cold dark matter, CDM. Dark energy accelerates the expansion of the universe, while dark matter drives the formation of structure. The only catch is that there is still no evidence for the existence of dark matter or dark energy. They are purely theoretical entities, and we may now have reached a point where scientists have to realize that the entire lambda CDM model may be based on errors. It is becoming increasingly likely that Edwin Hubble's idea of an expanding universe was wrong. They should have known it. Hubble saw it. It sounds strange, but the researchers should have known what was coming. The Hubble telescope has already discovered a galaxy in space that shouldn't actually exist. In January 2011, the news spread like wildfire through the world's scientific publications. Hubble had discovered the oldest galaxy ever observed in the cosmos, with a redshift of 10.3. This galaxy is 13.4 billion years old and therefore dates back to only around 420 million years after the Big Bang. However, the standard model of cosmology states that the first real galaxies were present in the universe around 1 billion years after the Big Bang. Initially, the discovery of the galaxy by the Hubble telescope was called into question. Scientists were eagerly awaiting Webb's launch in order to look even deeper into the universe and clarify the questions surrounding the existence of the very old galaxy. Webb showed the scientists what they needed to see: rows and rows of galaxies with z-values of 13, making them even older than Hubble's discovery. There may even be a galaxy with z equals 20. This galaxy, if its age can be confirmed, would be so close to the starting point that the theory of the Big Bang would no longer be tenable. Hubble sent cosmologists another warning. Shortly before Webb's launch in March 2022, scientists at Johns Hopkins University in the USA confirmed the discovery of the oldest single star ever observed. They named the exceptional discovery Earendel, the star of the dawn. Only 900 million years after the Big Bang, it must have been one of the first stars. Today we know that this star does not belong to the cosmic dawn because, as James Webb impressively showed, many billions of other stars in highly developed galaxies were already present